In this lesson, we're going to learn about integration by substitution. Let me just remind you in general that if you have a function, you take the derivative of it, you get a second function, that the integral is the reversing of the process. So if we integrated that second function, we would get the first function back. With this dynamic in mind, let's take a look at this example. So here's a function. Let's go ahead and take the derivative of it. And that, you may recall, requires something called the chain rule. The chain rule applied to many situations, one of which was a function to a power, such as a function to the 100th power. When we learned about the chain rule, we learned that the 100 would essentially come down in front of the function, decrease to a power of 99, but then the chain rule dictated that we multiply that result by the, quote, derivative of the inside function, which, as you can see, is 8x minus 24. I could simplify this thing here by rearranging the order of multiplication and then distributing the 100, but this is essentially what the derivative of the function on the left would be. So suppose, reversely, that we were asked to integrate the result of that derivative. Then, of course, the integral of that would be the original function that we started with. Now, this is not what integration by substitution is. This is just somewhat of a reminder of the chain rule and how it works and how it could be applied in reverse to do an integral. Let's take a look at this particular integral here. It looks a little more complicated probably than most integrals you've ever seen. I want to start this integral by reminding you that integrals don't distribute to a product of functions. You'll notice the times sign in this problem, and while it's very common for the typical calculus student to say, oh, I can integrate a product by simply integrating each of them and then proceeding from there, it turns out that's not true. Integrals don't work that way on products, except in rare cases, not one of them. So if the integral doesn't distribute to a product like this, that then becomes the question of what do we do to integrate a product? Well, there are many options, but one of them we're going to learn two different ways in this particular short video. The first method I want to talk about is the guessing method. Now, just to give you a warning, this method only works for, I would say, at most 1 in 5 students. So 4/5 of you or so listening to this video right now are going to find this very confusing and useless. But for those of you who find this method usable, it will be a very valuable tool. If you get lost anywhere in the guessing method, don't worry, we're going to go on to something called substitution, which is a more formalized method later. But let's think about what the guessing method would have us do here. We're trying to find an integral here, which is also known as an antiderivative. That means I need to fill in this blank. I need to know the derivative of what would equal this function. Now, some students, see if you're one of them, have a knack for guessing. Essentially, what we're going to do here, the guessing method of integration, is just filling in the blank with something you think that would logically have a derivative that equaled the right side of this equation. One thing that crossed my mind is that I could have this 3x squared plus 8x plus 7 raised to the 3/2 power. After all, the radical is the 1/2 power, and when we take a derivative, the exponent decreases by 1, so it makes sense to think that we might have something like this. Now remember, this is just a guess. There's no science to this or procedure. But let's take the derivative of our guess here in red and see if it works out. So when we take the derivative here, we use the chain rule. The 3/2 comes down, decreases by 1, making it the 1/2 power, and then the chain rule says we have to multiply by the derivative of the inside function. That would be 6x plus 8. Now, if you rework this function a little bit, writing the half power as the radical and doing some other basic algebra, you get this. And the question now is, does that equal the original problem? Well, no, it doesn't. But the nice thing about the guessing method is that if you guess close, you'll notice that your wrong derivative is actually quite often just a real multiple of the thing that you're looking for. This answer here seems to be exactly 3 times what we're looking for. And if that's the case, then maybe I should take my original guess and replace it with 1/3 of its original value. If you're already panicking and have no idea what's going on, just remember this method doesn't work for most people. The substitution method will save you if you're completely lost at this point. But for those of you who aren't, let's continue with the guessing method. I've now guessed that my answer would be 1/3 of my first guess, and this is going to turn out to work. So we're going to take the derivative of the thing in blue. The 3/2 is going to come down, decrease by 1, become a half, and the chain rule applies as before. Then, if you do some little cleanup on this algebraically, you'll see that it equals this. The work's not shown here, but it does in fact equal that function that we wanted it to equal. And therefore, our integral is that function which we would take the derivative of to equal the one we were given. And that's the end of the guessing method. Now again, it's a rare student for whom this works, but if you happen to be one of them, then it's worth knowing that you can always guess on an antiderivative problem, on an integral problem. Let's now take a look at the process called substitution. Substitution is a process invented to save you from having to guess at what the integral of this might be. So it's the same problem, we're going to get the same answer, but we're going to look at it from a slightly different perspective here. There is, however, a little bit of an element of guessing in the substitution process. The first thing you do in the substitution process is pick something inside of the problem, inside the function we're integrating, and give it a different name. U is traditionally the name that we give it. So I'm going to take 3x squared plus 8x plus 7, which is part of the original problem, and I'm going to call it U. Nothing special about that letter. You could call it your first initial. You could call it Y. You could call it theta. It doesn't make any difference. Now, there is still an element of guess and check in the substitution process. For example, you might try, if you didn't know any better and you're brand new to this subject, you might just as easily have picked something else in the problem to be U. Or maybe you picked this part of the problem to be U. And it turns out those two U's on the top lead to something that doesn't work, whereas the U on the bottom does work, which brings up an interesting question. When you're doing substitution and you're on step 1 and you have to choose something in the problem and call it U, what do you pick? Well, there's really no way to know, except to try and see if the process happens to work. Although usually, if I have two polynomials in the problem, I will typically pick the one that's a higher degree. That may be some good advice on how to choose your U. But again, there's no way to know for sure. Now, here's how substitution works. Once you've chosen your U value, you then take the differential of both sides as shown. Essentially, take the derivative of your guess. By the way, this would be the same as this statement here. The derivative of U with respect to x, or the derivative of my choice that I've chosen for U, is 6x plus 8. In any event, once you've taken the differential, your goal now is to take your original integral and completely convert it out of the letter x and into the letter U. The goal here is essentially to change this to a U integral, an integral having no x's whatsoever. Well, the first thing that we can do, obviously, is replace our choice of U with the letter U. But we still have x's in this integral, and in order for substitution to be a productive, useful process, you have to somehow be able to get rid of the original letter completely, which in this case is x. One thing I like to do is sort of physically separate my u's from my x's, not that that changes the value in any way, but it gives me kind of a goal. Now, at this point in the substitution process, you have to have this keen sense that you can use this trick called the multiply by 1 trick. What do I mean by the multiply by 1 trick? You'll notice inside of this integral, I've multiplied in a half times 2. And that may seem really strange, like, why on earth are we inserting a half times 2 here? Well, before I tell you why we're inserting a half times 2, let me just justify that it's a mathematically legal and valid choice. Everyone knows that 1/2 times 2 is 1. So all I'm really doing here is multiplying the integral by 1. Of course, you might ask, that's fine. I understand that it's legal, but why? Why not a third times 3, or 1/4 times 4, or 1/5 times 5, or many other things whose product is 1? Well, you see, by choosing a half times 2, I can then distribute that 2 into the parentheses. And by distributing that 2 into the parentheses, you'll notice that I now have the original derivative of my choice. I now have a 6x plus 8 in the problem. And if you look up here in the right corner, the fact that 6x plus 8 dx is equal to du allows me to replace 6x plus 8 times dx with du. Now, this leaves many students feeling very uncomfortable because it leaves them with the feeling that, and see, you can sort of analyze your own brain and see if you're feeling this right now. You might say, well, Professor, I understand all the math that I'm witnessing right now, but I personally never would have chosen 1/2 times 2 as my 1. And that does add an element of sort of tricky cleverness to these problems. But it was the 6x plus 8 we were trying to get. So it seemed like a logical choice of 1, because then I could take the 2 and distribute it and get the 6x plus 8 I wanted. But look at the very bottom line here. We no longer have the letter x. That is the beauty of substitution. So what have I done? If you look at the top of your screen, I have this big ugly integral with x's. If you look at the bottom of your screen, you'll notice I now have a very small and maybe easily doable integral with the letter u. And since these integrals are equal to each other, I can just do the one on the bottom rather than having to do the one on the top. So I'm going to take this thing here, and I'm going to now calculate that. Remember that the square root of something is the same as the half power, and this allows me to use the power rule. Applying the power rule and doing some basic fraction arithmetic from high school ultimately leads me to an answer. Now, while this answer isn't wrong, it isn't finished, because this answer has the letter u in it. One of the reasons that we substituted a big ugly expression for u is to make the integral simpler, which is fine. But look at the original problem. They're asking me for an antiderivative of a function of x. I certainly can't have a u in my answer. That wouldn't make any sense. But we're almost done here, because after all, u equals this quantity. Therefore, I can replace the u in my answer with that quantity, and I now have the antiderivative, the original problem. And you notice there's no u's in my answer, nor should there be, because I wasn't asked to integrate anything with the letter u in it. The letter u was just a transition to turn a hard problem into an easy problem.